In chapter 11, we will be looking at oxidation reactions of organic chemistry. So in this lecture, we will cover the following. First of all, we'll define oxidation. Next, we will determine oxidation states of different carbon atoms. Why carbon atoms? Because, of course, organic chemistry is the study of carbons, or compounds that contain carbons. Next, we'll look at some oxidizing agents, examples of that. And we'll look at the oxidation of two very important functional groups in organic chemistry, and that is the alcohols and aldehydes. And lastly, we'll look at the oxidation of 1,2-diols. Oxidation is the supply of oxygen. And in organic chemistry, we take it further to say that it's also the removal of electrons, usually accompanied by the loss of hydrogen. So again, supply of oxygen, removal or loss of electrons, and also hydrogen, typically hydrogen. So the oxidation of hydrocarbons, methane and butane, we're very familiar with that because the oxidation process liberates heat. And of course that heat is very useful for cooking and heating our homes in the wintertime. So here are two examples here. Methane reacting with oxygen gives, of course, carbon dioxide and water, but equally important, it liberates a lot of heat per mole. Same for butane, liberates heat. I should point out also that this type of oxidation reaction is also known as combustion. That's the reaction with oxygen. Let us turn our attention now to the oxidation states of carbon atoms. It's important to know the oxidation states of carbon atoms because after a reaction it typically changes, or it changes essentially, especially if it's an oxidation reaction. So let's see how one way we can calculate the oxidation state of a carbon. So let's concentrate on this central atom here, carbon. We know that carbon has 4 bonds to it, and here is a carbon that's bonded to another carbon, and we know that there are 2 electrons in a single covalent bond. So what we try to do here is to assign electrons to this carbon based on the bonding. So if there are 2 electrons in the covalent bond to another carbon, since they are of equal electronegativities, we assign 1 electron to this carbon or this alkyl group and 1 electron here to this carbon. Same here. If carbon is bonded to hydrogen, however, we know that carbon is more electronegative than hydrogen, so the 2 electrons for this covalent bond, we assume that it is more associated with this carbon. So here we have 2 electrons that are associated with this carbon for this bond. Next, look at this bond. This carbon is bonded to oxygen. We know that oxygen is a lot more electronegative than carbon, so the 2 electrons in the covalent bonds are more associated with this oxygen than the carbon, so we assign 0 electrons to that carbon. So the number of electrons that are associated with this carbon in terms of calculating its oxidation states would be 2, 3, and 4 electrons, and you subtract that from 4, which of course is the oxidation state of carbon as shown on the periodic table, so that's 0. So the oxidation state of this carbon here is 0. The oxidation state of this carbon in this hypothetical molecule here is a little different, because this time the carbon is bonded to 1, 2, and 3 alkyl groups, or 3 other carbon containing groups. So therefore the number of electrons that are associated with the central carbon are now 1, 1, and 1. We know this is 0 because this is oxygen. So the number of electrons that are used for calculation would be 3, and of course 3 from 4 is plus 1, so therefore that is a plus 1 oxidation state. We can do the same here. Oxygen, more electronegative, oxygen, more electronegative, 0 and 0, alkyl group, 1. So the number of electrons associated with this carbon in terms of the calculation of an oxidation state is 1. And of course 4 minus 1 is 3, so the oxidation state here is plus 3. Let's apply that concept. So here we have a molecule, hypothetical molecule here, where we have R and 2 hydrogens as a primary alcohol. Oxidizing agent, oxidizing it to the aldehyde. So notice a primary alcohol is now being oxidized to an aldehyde, and the oxidation state goes from -1, which you can calculate based on the previous slide, to +1, which you can also calculate. So there's a change in oxidation state from -1 to +1. Further oxidation changes it to a carboxylic acid, of course, as we know, and that oxidation state of this carbon is now +3. So the observation is that in oxidation, the number goes more positive. The oxidation number for the carbon, if it goes in a positive direction from here going up, it's an oxidation. So in other words, for this reaction, this goes from -1 to +1. So therefore that goes up or increases in a positive direction. So therefore this molecule is oxidized. You can do the same here and you can go on. One thing I wanted to point out here, which you'll see again, is that in going from this primary alcohol to the aldehyde, hydrogen is lost. 1 here, and in going from the aldehyde to the carboxylic acid, the hydrogen that's bonded to the carbon is lost. So there's a loss of hydrogen. You may recall when I said the definition of oxidation is the loss of hydrogen in addition to loss of electrons and the supply of oxygen, but there's a loss of hydrogen bonded to the carbon. Same here. Here's a hydrogen for this secondary alcohol, and it's oxidized to the ketone, and there's no hydrogen. So that means that if you had a tertiary alcohol and you supply an oxidizing agent, there should not be a reaction because there's no hydrogen bonded to the carbon to be lost. So let's look at some more examples before we look at the mechanism. So here's a primary alcohol, 2 hydrogens, in an oxidation using sodium dichromate in sulfuric acid. They're both lost, and the oxidation state goes from -1 to +3 to form a carboxylic acid from the primary alcohol. Look at this one, the aldehyde, same oxidizing agent, sodium dichromate in sulfuric acid. The oxidation state here of this carbon is +1, and it goes to +3, increases in oxidation state, goes from an aldehyde to a carboxylic acid, a different functional group using a oxidizing agent. Another example. This one is potassium permanganate in potassium hydroxide. Secondary alcohol goes to a ketone, change in oxidation state. A tertiary alcohol, no hydrogens bonded to this carbon. Notice no hydrogens bonded to that carbon, therefore no reaction. We'll have to look at the mechanism to see why there is no reaction if there is not a hydrogen bonded to this carbon. Now you can see the importance of knowing or understanding the mechanism of a reaction. It's not just memorizing if it's a tertiary alcohol, there's no reaction. That's one way, but the better way is to understand how these reactions work, which we'll look at in a second. Let us look at another example here. So this primary butanol, in the presence of a strong oxidizing agent, goes to the aldehyde, but because there's a hydrogen here, it is quickly oxidized in the oxidizing agent to give the isolated product, the final product of butanoic acid. So if you have this primary alcohol and you react it with potassium permanganate in potassium hydroxide, this is the product that you will isolate. Let us look at the mechanism to see how it works, number one, and the importance of having that hydrogen bonded to the carbon. Here's an alcohol. Here's a hydrogen that's bonded to this carbon. In the first step of this mechanism, potassium permanganate, as you can see here, this is the Lewis dot structure. This manganese here is bonded to 4 oxygen, which means that this is very electropositive. So we have electrons here. It will attack this very electropositive here, manganese, to produce this. As you can imagine, this base will attack this proton here to neutralize it, to get this as an intermediate, and of course water is liberated in the process because we've lost an oxygen. Equally important here for this reaction to occur is that this base that's present abstracts this hydrogen, just the hydrogen without its electrons, and then these electrons here, as you can see, they swing in and these electrons go out onto the manganese, breaking this bond here to form the carbonyl compound here, and of course here is the other inorganic product. So now you can see the need for this hydrogen here bonded to the carbon that has the OH group for the oxidation reaction to occur. So that is why we need a hydrogen bonded to the carbon that has the alcohol group for the oxidation reaction to occur. Let us look at another oxidizing agent, sodium dichromate, which we have seen before. As we all know, a practical use of this oxidizing agent is it takes ethanol or oxidizes ethanol into acetic acid. And of course, in the process, the reddish dichromate changes color to green. So in the breathalyzer test, if one consumes too much alcohol and it's tested using the dichromate reddish color, if that changes to green, that means an oxidation occurs, which means that or implies that alcohol in the form of ethanol was present and it was oxidized to acetic acid. So that's one of the practical application of the oxidation reactions here. Let's look at the mechanism for the dichromate. So here's chromium. As you can imagine, chromium bonded to electronegative oxygens here. So it's very electropositive. And here we have a aldehyde. Notice the hydrogen here. So these electrons, the nucleophilic electrons here, will attack the chromium to give this intermediate here. Water is present, can form this intermediate here. Again, same aspect here as before. Water in this case, not OH negative because it's an acidic medium, so you will not have OH negative present, but you will have water, which of course has 2 electrons, as you know. It can abstract this hydrogen as a proton, leaving again these electrons here to form a double bond here and kicking this out here as the inorganic product. So once again, this hydrogen here plays an important role in the oxidation. In this case, it's an aldehyde that's been oxidized to a carboxylic acid. The question you may be asking at this point, is it possible to take a primary alcohol and oxidize it to an aldehyde? Because of course, as you know, in chemistry, especially organic chemistry, we need aldehydes at times and not the carboxylic acid. So it would be nice if we could start off with a primary alcohol as a starting material and stop the reaction at the aldehyde stage and not go on to the carboxylic acid. There's special oxidizing agents which are much milder that can be used to oxidize the primary alcohol to the aldehyde and not go on to the carboxylic acid. Here's one. It was discovered by Swern, so it's known as the Swern oxidation. So as chemists, we understand the Swern oxidation. Here are the ingredients or the chemicals for that, the reactants. Oxalyl chloride. Let's look at that for a second. It's a carbonyl bonded to electronegative chlorine, which is a good leaving group. Electronegative chlorine, a good leaving group, and also oxygens and oxygen over here, which are very electronegative. Another reagent that's present is DMSO, dimethyl sulfoxide. We'll see the importance of that in a second when we look at the mechanism. And in the reaction, as a second step, a base triethylamine is added. So once again, this reaction involves a primary alcohol being oxidized to an aldehyde using this as the oxidizing agent. So it's best to understand how this oxidizing agent here, how it works. So let us look at the mechanism. In the first step, as you can imagine, the electrons that's on the oxygen of DMSO attacks the very electropositive carbon here. Chlorine is a good leaving group because it's a very stable conjugate base. So it leaves. As you can see, the arrows here indicate electron movement. So these 2 electrons here attack this carbon to form a bond, as you can see here. And of course, this chlorine leaves. As you can see, it is gone, and here it is. This is an intermediate, not the product. So this chlorine can attack this to form a neutral intermediate here. This neutral intermediate is not stable. Why isn't it stable? Looking at it, you can see potential carbon dioxide right here. So in this reaction, if these electrons came in to form a double bond right here, what we have is carbon dioxide, providing these electrons break to give carbon monoxide right here. And then this chlorine, as you know, is a good leaving group. It can exist by itself because it's a stable conjugate base. So this intermediate here quickly reacts or disintegrates to give carbon dioxide right here and carbon monoxide right here. as we have seen before, and Cl right here, and this is the intermediate that's left here. It's called a chlorosulfonium salt. That chlorosulfonium salt now reacts with the alcohol. Because you can clearly see a positive sulfur, and you can see here electrons that's on the oxygen, so it will react to form this bond right here. Notice again the electron movement. These electrons move over to bond, and this chlorine here leaves as shown here. So this is an alkyl sulfonium salt, a salt again because we have an anion and a cation. Here's where the base becomes important. The base can abstract a proton. Remember an acid-base reaction? An acid-base reaction involves the base abstracting a proton to form a conjugate acid. What's left behind is, of course, a negative charge on this carbon. You can see here that a negative charge on a carbon adjacent to a positive charge on a heteroatom is called a ylide. You've seen a phosphorus ylide before when we looked at the Wittig reaction. So this is an alkyl sulfonium ylide. Okay, in the last step of the reaction, as you'll see here, this ylide quickly breaks apart because it abstracts this hydrogen here, and then this bond breaks to give us the carbonyl compound as we have seen here. So here's the carbon, here's the double bond that's broken here, and here is the other product, which is dimethyl sulfide. So again, you need not know the mechanism, but understand how it works and the importance of the different reagents. As you can see here, the oxyl chloride is very important because of that electrophilic carbon. Dimethyl sulfoxide is very important because it's going to supply literally that oxygen, oxidizing agent, and of course the triethylamine is very important because it's going to abstract that proton to form the ylide. So as a summary, you take this primary alcohol, you can oxidize that to the aldehyde, benzaldehyde, using the Swern oxidation. There's another reagent, or milder oxidizing reagent, that can be used, and this is called the Des-Martin oxidation, named after two chemists, Des and Martin, who developed this oxidation reaction. And here is the main ingredient. It's just called the DMP. Here it is. The mechanism is in the book, but you can see again it has a base. Here we can take a primary alcohol and we can oxidize it to the aldehyde. So here all you need to put is DMP, or Des-Martin reagent, and don't forget, in the second step, the base, triethylamine, going from here. So now you have a choice. You can use either the Swern oxidation or the Des-Martin oxidation to go from a primary alcohol to the aldehyde. Let's look at a third possibility. Here is pyridine chlorochromate oxidation, or PCC. So what we have here is pyridine chlorochromate. This is going to be your oxidizing agent, mild oxidizing agent, in the presence of a solvent such as dichloromethane. It can take an aldehyde, a primary alcohol, to an aldehyde. Notice it maintains the functional group here in a molecule, another functional group. So if it's a difunctional molecule, as shown here with the unsaturation, this reaction will not affect the carbon-carbon double bond, but it will just oxidize the primary alcohol to the aldehyde. So you can just put PCC in CH2Cl2 dichloromethane in terms of showing that oxidation. So let us look at the summary. So here is a primary alcohol, as you can see. You can use PCC in the presence of dichloromethane to give you the aldehyde. Here is another alcohol. This time it's a secondary alcohol. The nice thing about these reagents is you can use the same reagent to oxidize it to a ketone. If, of course, this is a secondary alcohol. If it were a primary alcohol, it would stop at the aldehyde stage. And here, of course, is our benzyl alcohol. And, of course, this, as you will recall, is the Swern oxidation. And we can stop at the aldehyde. So this gives you choices in terms of oxidizing reagents that can be used to transform reactant alcohol into a product such as the ketone or the aldehyde. Let us look at another type oxidation, and this one is the periodic acid, HiO4. As you can imagine, it's a strong oxidizing agent because it has 4 oxygen atoms bonded to it. It is very selective, however. It will oxidize molecules or alcohols that are 1,2 diols. In other words, the diols will be on carbons 1 and 2, or adjacent carbons. If the alcohols are on adjacent carbon, this periodic acid will oxidize by breaking this bond here and forming a carbonyl. So the OH here goes to a carbonyl. This OH here goes to a carbonyl. Notice again, there's a change in oxidation state if you were to do the calculations for the oxidation state for each carbon. So here's another example. This time we break this bond with periodic acid, but notice here this carbon here is different from this carbon because this has a methyl group. So here is this carbon here, and this carbon has a hydrogen, and here it is. So if you had this molecule as an unknown, for example, one practical application of this reaction is that you subject it to periodic acid. If you get this as a product, and you can determine the structure from your spectroscopy, the infrared and NMR, for example, if you know this is the structure of the product from the oxidized reaction, you can deduce that this is the structure of your unknown compounds. By the way, the tutorial set that you'll get shortly will have examples like this. Some other oxidations that you'll see that you are pretty much familiar with is the Tollens test. Here we have an aldehyde, and you react it with silver ions. After the oxidation, what you get is silver element, which appears as a silver mirror. Of course, as you know, silver has a very shiny color. So if you do this reaction, if your unknown, for example, had an aldehyde functional group and you reacted with silver ions here, if you get a silver mirror, one conclusion is that the unknown starting material was an aldehyde because of that specific reaction. And that's called the Tollens test. I'm pretty sure you'll do the Tollens test in your lab. Another practical oxidizing agent is the sodium nitrite, and it can oxidize aniline, for example, to an azide salt, and these azide salts are very important compounds in the dye industry. We'll see more of that when we look at aromatic chemistry. So let us look at the applications of these reactions. So let's see. Of course, as you know, one of my emphasis here is knowing the concept And equally important is, can you apply that concept to solving a problem? So let us see if we can apply the concepts that we have just learned from this lecture to solving this problem. Show how to carry out the following transformation. Synthesis. So here's your starting material, and you need to supply appropriate reagents and steps. So when this is done, you have here this as the aldehyde. As I pointed out, as chemists, and equally important, as scientists, you do not know the answer just off the top of your head, but as scientists, we solve problems using the scientific approach. An important aspect of the scientific approach, as I pointed out earlier, is observation. So let us observe this reaction by starting with the product, the target molecule. One observation is that there is a new carbon-carbon bond right here. So we have introduced another carbon. We look at the reactant and we see that it has one carbon less than the product. And this is a carbonyl. So right away you start thinking, how can I convert a carbonyl, carbon-oxygen double bond, into a carbon-carbon bond? You know, you can do that from the Wittig reaction. We can make a double bond. Another observation of the product or the target molecule is that there is an aldehyde functional group. So again, you should analyze your target molecule in terms of functional groups. This is an aldehyde functional group. So a question you should be asking is, how do I make a aldehyde functional group? You know, you can make an aldehyde functional group from the oxidation of a primary alcohol. You have a slate of reagents that you can use. PCC, Swern oxidation, or the Des Martin reagent. So now all you have to do is to put all of this information together and communicate that to solve this problem. As I've pointed out earlier, a key aspect of scientific training is communicating scientifically. So we communicate by using figures and reactions and tables, etc. So let's see how we can communicate what we have observed and come up with applying that strategy to solving this problem. So we can make the aldehyde functional group working retrosynthesis, working backwards. We can make the aldehyde functional group using the Swern oxidation of a primary alcohol. So if you had this molecule here, you can oxidize it using the Swern oxidation to make your target molecule. This molecule has an alcohol. You can say, how do I make alcohols? You learned from the previous chapter, one way of making alcohols is by the hydration of alkenes. In this case, if you had this alkene, you can carry out a hydration. In this case, it's the antimechanical hydration, where we will use here this set of reagents, diborane or BH3 in the first step, and the second step an oxidation, H2O2 in sodium hydroxide. And then you say, how do I make this alkene from this ketone? You will recognize right away that a Wittig reaction is one that can carry that out. So this is what I would expect you to communicate in terms of carrying out the transformation of this as your starting material, going to your target material here. So once again, I think this is the end of it. Yeah, that's the end of this lecture. So once again, make sure you understand the concept. I just recognize a typo here. which I'll have to fix. This is a chloride. I'll get that fixed. So once again, know the concepts, but equally important, know how to apply the concepts to solving problems of this type. I will post another lecture video on chapter 11 shortly, so look out for that. So continue to study hard as we conclude the semester. I know it has its challenges, but we're almost there, so continue to study hard. Okay? Bye.